Now that we have talked about methane, a polyatomic molecule with sigma bonds only, and now that we have got an idea that we can generate molecular orbitals that are delocalized over the entire molecule, but they can give you an idea about the electron density between two given atoms. The field is set for a discussion of molecules that have pi bonds, and we will start with the simplest such molecule that one can think of, and that is ethylene. And here we are going to use this kind of a cartoon notation always. Here we are actually drawing these constant probability surfaces the way they are usually drawn in textbooks. And our notation is going to be that we are going to denote the p orbitals, the atomic p orbitals as chi's, chi 1, chi 2, chi 3, whatever is required, and we are going to denote the molecular orbitals as psi's. So, before we do that, let us discuss in very brief what pi electron approximation is. First of all, the structure of the molecule is considered to be built by the sigma framework, and while building this it does not matter whether one has used valence bond theory or molecular orbital theory, whether hybrid orbitals have been used or not. The structure of molecule is supposed to be in place. So, pi bonding comes into play only after a sigma bond is established. That is the realm of this theory. We are not talking about molecules that have exclusive pi bonds only, right. So, the pi framework has to be defined first, the sigma framework has to be defined first, and pi electrons are considered to move in a fixed effective electrostatic potential involving sigma electrons. Not due to, but involving sigma electrons. What does it mean? That means there are a number of nuclei. So, if you take a pi electron, a given pi electron, they are considered to move under the joint field of this nucleus, but this field is shielded by the remaining electrons. Remember when we talked about particle in a box, we had said that we can approximately describe conjugated polyenes by a particle in a box model, free electron model. There also the consideration was that there is shielding of the nuclear charge by the remaining electrons when we talk about any given electron. Here we are considering that the shielding is such that it is not complete. The electron does not become free as long as it is in the molecule. The potential energy is not equal to 0 necessarily, but there is shielding, effective electrostatic potential is there. And in this framework pi electrons are delocalized all over. The method to do this, the simplest method is Huckel molecular orbital theory. Huckel U has actually 2 dots on top of it, and this is a semi-empirical approximate method. As you will see, we will not make any attempt to write down the Hamiltonian completely. We will not make any attempt for an exact solution because it cannot be achieved. Rather, we will use certain experimental conditions, experimental considerations to build our semi-empirical approximate description of these molecules in question. With this background, let us discuss ethylene. And remember, when I say let us discuss ethylene, I mean let us discuss the pi electrons of ethylene. So, this is the cartoon that we had shown you earlier. The pi wave function will be written as psi phi is equal to C1 chi 1 plus C2 chi 2, where chi 1 and chi 2, as we said earlier, are the 2 p orbitals of the 2 atoms here. C1 and C2 are the coefficients. Before going further, is there any reason why the magnitude of C1 should be any different than the magnitude of C2? Actually there is not. By symmetry, I mean 1 and 2 are arbitrary labels we are using, we can interchange them. So, there is no reason why either of these coefficients will have more or less magnitude than the other. Remember, square of coefficient is the contribution of that p electron in the pi molecular orbital. Square of coefficient is the contribution of that p orbital in the molecular orbital, in the pi molecular orbital. So, there is no reason really why mod C1 should be anything other than mod C2. So, we are going to work this out more formally, but I hope we understand this clearly. So, we might as well take C out and write C multiplied by chi1 plus minus chi2. That is the kind of wave function we are going to get. That is something we can sort of guess even before going into any further. Okay. Now, let us write Schrodinger equation H psi equal to E psi, very simple. In the next step, let us expand the wave function. Hamiltonian, what is the Hamiltonian here? Hamiltonian, remember we are saying that any electron that we talk about is considered to be moving in an effective potential provided by all the nuclei in question and the other electron. So, if I am talking about chi1, well if I am talking about electron in on the first atom, then I am talking about this electron moving in the field of nucleus 1, nucleus 2 and electron 2. Okay. That is what the Hamiltonian is. If you want, you can write down the expression, we will not do it because we are not going to make any attempt to actually solve it exactly. Alright. So, Hamiltonian operates on C1 chi1 plus C2 chi2 to give us E multiplied by C1 chi1 plus C2 chi2. Is chi1 or chi2 an eigenfunction of this Hamiltonian? No, they are not. They are eigenfunctions of the hydrogen atom Hamiltonian written in coordinates of 1 or 2. Is C1 chi1 plus C2 chi2 an eigenfunction of the Hamiltonian H hat? Yes, it is. The combination is an eigenfunction. That is why we have been able to write the Schrodinger equation in this form. The only trouble is that there is no direct way of solving this and finding E. So, we are going to try an indirect method that is used very commonly in quantum mechanical problems. What do? We left multiply by chi1 and integrate over all space. We are trying to generate two different equations. Why? Because we do not know what the mixing coefficients are C1 and C2, two unknowns, we need two equations and this is how we generate them. For the first equation, left multiplied by chi1 integrate over all space. What do you get? Integral, well C1 multiplied by integral chi1 H hat chi1 plus C2 multiplied by integral chi1 H chi2 is equal to E multiplied by C1 integral chi1 multiplied by chi1 over all space plus C2 multiplied by E integral chi1 chi2 over all space. In bracket notation, this is what we get. Please make sure that you understand how we get this expression, how we get this equation. C1 integral chi1 H chi1 plus C2 integral chi1 H chi2 equal to E multiplied by C1 into chi1 integrated over all space plus E multiplied by C2 integral chi1 into chi2 integrated over all space. Okay. Do we know how to find out these integrals? We actually do not, but we can at least give them some names. So, the first one integral chi1 H chi1, I call it H11. In general, integral chi H chi is going to be called Hii. Then integral chi1 H chi2 is given the name H12. I hope you can see the pattern here. The name of the integral is H from Hamiltonian, subscript of the first wave function, then subscript of the second wave function, like that. On the right hand side, we call integral chi1 over all space as S11. Of course, I hope it is not very difficult for us to realize that this S11 is going to be equal to 1, because chi1 is a p orbital that is normalized. And another thing, here we are working with real p orbitals. We are working with px, py, pz. In this kind of a molecule, it is more convenient if you talk about the molecule in xy plane and you consider chi1 and chi2 to be along z axis. So, of course, that is going to be 1, but for some time let us retain the notation S11 because then we get some nice good looking symmetric expressions. So, we will just keep it for now. And integral chi1 chi2 is S12, and that also you know, right, overlap integral as we have encountered in our discussion of H2 plus. The only difference is that for H2 plus the overlap integral came from this kind of an overlap head on, here we are talking about this kind of an overlap side on. Okay. So, let us write this equation in terms of these integrals and let us bring everything on the right hand side to the left hand side. So, that on the right hand side we are left with 0. What do we get? C1 multiplied by H11 minus ES11 plus C2 multiplied by H12 minus ES12 equal to 0. So, a linear equation in which the variables are C1 and C2 and the coefficients are H11 minus ES11 and H12 minus ES12 respectively, right. So, that is the first equation that we sought. How do we get the second equation? Same thing, just left multiply by chi2 and integrate over all space. I encourage you to please do it yourself and convince yourself that the expression you get is this. And when you do that, one thing that should come to your notice is that here I have written H12, actually I should have written H21 because I am left multiplying by chi2. So, the p orbital in the bra vector is actually chi2 and not chi1. Why have I written H12? Well, without going into further detail, believe me when I say that utilizing the properties of Hermitian operators, H is a Hermitian operator, remember H12 is equal to H21, it comes from something called turnover rule, and S12 of course will be equal to S21 because it is just integral of a product of two functions, f1 f2 and f2 f1 give you the same thing. Alright, so we got two equations and we have two unknowns C1 and C2. So, we should be able to in principle solve this and get expressions and find out what C1 and C2 are. Let us write this system of linear equations as a matrix equation like this. Square matrix containing the coefficients multiplies a column matrix containing the variables to give us a column matrix elements of which are 0 and 0. Now see, how do I solve this equation? One solution is that C1 is equal to 0 and C2 equal to 0, but if that is the case then there is no mixing, yeah, there is no wave function because psi pi is going to be 0 into chi1 plus 0 into chi2. So, there is no wave function, that is a trivial solution. How can we hope to get a non-trivial solution, a non-zero value of C1 and C2? Well, this can exist if this matrix cannot be inverted. The square matrix here, if it is such that it cannot be inverted, that is the only hope of getting non-zero solutions for C1 and C2. What is the condition for an inverse of a matrix to exist? The condition is that its determinant should not be equal to 0. Here we want the opposite thing, we want the inverse to not exist. So, the condition is that the inverse of the square matrix should not exist, therefore, this determinant of the square matrix should be equal to 0. When this determinant equal to 0, the inverse does not exist and that is the only hope of us getting C1 and C2 that are non-zero. So, this determinant is called the secular determinant and secular determinant equal to 0 is called a secular equation. So, for the rest of the discussion we are going to try to see how one can solve for this secular equation.